Again, good evening, everyone. It's officially 6 p.m. and we're about to start our workshop. Um, I am very glad to have all of you here. We have currently we have like 90 people inside this Zoom call, but we're expecting, or at least based on the invites, the number of those who registered, we have about 176 invites who are or registrants who registered for this workshop. So this was supposed to be a workshop just for our lab, the Center for Computational Imaging and Visual Innovations. I think just yesterday or just 2 days ago, we have like only 37 registrants. But when the ADRIC shared this invite, I think we were able to get like times 4 of the number of registrants. So the goal of this workshop, by the way, for the sake of everyone, is for our lab to train our incoming students. So, and the other thing is some of the other labs under DLSU CCS also requested that their members, their students, be invited to some of our computer vision related workshops, no, like this one. So we created this technical workshop, and this is a series of workshops to help our students implement certain computer vision topics. Okay, and this is, as I've said, the first of its kind and the first offering for this term and all throughout all of the other offerings. So um, I will be introducing our speaker for today and the content of the workshop. So the title of the workshop is Building an Image Classifier Using PyTorch. In this talk, the speaker, Joseph, will give an overview of the PyTorch machine learning framework and how to build a simple model for image classification. So we want our students to learn how to implement a simple image classifier using convolutional neural networks. He will discuss the process of preparing the dataset, importing pre-trained models, and setting up the overall training and testing loop. We also gave out the outline of the workshop. So the first is we're going to learn how to prepare the PyTorch environment, how to prepare the dataset, loading of pre-trained PyTorch models, loss functions and optimizers, and how do we do training and testing loops. Um, the thing that we weren't able to include in the invites are the requirements, not really the requirements, but the prerequisite, no, the prerequisite knowledge of those who will attend this workshop. So we're expecting students to have at least an idea of the general machine learning framework. No, they should know what a loss function is, what are optimizers, and yung gradient descent. Um, they know what training and testing means. Um, the basic training loop, no? So dapat meron ng idea how a machine learning model learns from the data set because our technical workshop will not cover that. And as we mentioned, since this is a technical workshop, we'll be working on actual programming, no? We are going to code, we're going to program. You will watch Joseph discuss about how to program a certain image classifier. So we're not gonna discuss the theories behind this. That is for another workshop series. I think yun lang naman yung disclaimer ko for this technical workshop series. But I do hope everyone will learn a lot about the topic that we're going to discuss today. Um, I think that's it for my introduction. So let me introduce the speaker for today. So this meeting will be recorded. Siguro by the end of this meeting, just to give you an idea as well, aside from the demo code that we will show you today, we're also going to give all of the participants a copy of the code and an assignment file. So you do not have to submit the assignment, but at least that will help you um, learn, no, aside from the things that we are going to do here in the workshop. So meron kaming code for this workshop, meron ding assignment na pwede nyong sagutan in your free time. Now, the other thing that I forgot to mention, I sent out emails to, I think, the first 150 participants or registrants discussing what are the installation links for some of the modules that you'll need for this workshop. So kung hindi nyo na-receive yun, I think you only registered today. Kaya hindi nyo na-receive yung email. But I think Joseph will be discussing that as well later. Okay? So just to formally introduce ourselves, we're the Center for Computational Imaging and Visual Innovations. This is for the sake of our friends from outside of DLSU. I think we have participants from De La Salle pa. Some registrants are from Ateneo. There are students from UP. And I also saw some students from Adamson. So welcome to our workshop. Let me introduce the speaker. Our speaker for today is Joseph Thomas Anyo. Joseph is a fifth-year student from the College of Computer Studies of De La Salle University. He is part of the honors program, the BSMS program, and also a member of our lab. He is currently working on his thesis involving the design of an image classification model for the accurate classification of skin lesions. So without further ado, let me pass the floor to Joseph. Joseph.
Thank you, sir. I'll share my screen now. Right. So good evening, everyone. Once again, So good evening, everyone. Once again, I'm Joseph, and today I'll be managing this workshop to show you guys how to create a basic image classifier using the PyTorch machine learning framework. So I created a notebook for today. We'll be giving you guys access to it at the end of the workshop, but you don't necessarily have to code anything. Everything's already been placed in the notebook, so all you have to do is run it. So for now, you guys can focus on the main workshop presentation and as well as sort of the flow on how to create our classifiers and how to train them. So these are the contents that we'll be discussing for this workshop. The first is setting up the PyTorch environment. Second, we'll look at preparing the dataset. We'll also look at loading the existing models from the PyTorch library. And then we'll talk about loss functions and optimizers. And then lastly, we'll discuss the training and testing loop for our classifier. So if there are any questions, feel free to either unmute your mic or send them in the chat, and I'll try my best to answer them. So to start, let's look at first setting up our PyTorch environment. So I won't do a step-by-step guide on how to install each dependency, since it will depend then on the configuration of your device. So instead, I will provide you guys the main list of libraries that we need to install. And then I also provided links to reference materials that will help guide you in installing these dependencies yourself. So before installing any of these libraries, I suggest creating a virtual environment. So the reason for that is PyTorch uses some common libraries, for example, NumPy, which you may already have installed in your device. So when you install PyTorch, PyTorch also installs the NumPy version that it needs, and there's a chance kasi na their versions might conflict with each other. So to be safe, it's best to first create a virtual environment and download all the dependencies there. So to start, the first thing we need is, of course, Python. So PyTorch requires at least 3.6 or higher. The latest version of PyTorch, if I recall correctly, needs at least Python 3.8. The next libraries that we need is the PyTorch library, and then underneath that we have Torch Vision and Torch Audio. So PyTorch is the overall machine learning framework, while the Torch Vision and Torch Audio are sort of the additional libraries that we get our functions from. So I included here a link that leads you to the PyTorch website. So if we scroll down, we can see here there's a section wherein we can input the configurations of our device, and it will provide us with the installation command to install all these three dependencies together. So here for the PyTorch build, we can select the stable version, and then you select your OS. For the package manager, you select whichever package manager you're using. So for me, I personally use Conda. For the language, we select Python. And then for the compute platform, I'll discuss this later on. So for PyTorch actually requires PyTorch supports both CPU and GPU. But for the GPU, I believe it only supports NVIDIA GPUs. So for Mac users and people that don't use or don't have an NVIDIA GPU, you're limited to only using the CPU version, which isn't necessarily bad, but keep in mind na lang that you'll be limited in terms of training since it will take significantly longer and it will be more resource intensive on your end. So for the compute platform, this will depend on the version of the CUDA toolkit that you've installed. So CUDA is the software that allows PyTorch to access our GPUs. So without CUDA, we won't be able to use our GPUs for training. So in the notebook, I also included links on how to install CUDA. So the first link will lead you to the website wherein you can see the different versions of the CUDA toolkit. It doesn't really matter which version you pick as long as it's supported by PyTorch. So any one of these versions should work. And then the installation command is straightforward. So I don't think you'll have any problems installing them yourself. So of course, you pick the operating system and you simply just follow the installation instructions. The second link takes you to a site that checks where you can check the compatibility of your GPU. So you don't necessarily have to worry about this too much since I believe most of the modern NVIDIA GPUs are compatible with PyTorch. So you don't have to worry about this too much. So those are the main dependencies that we need to install. Once we install them, we can run this block of code. So I'll run it. And this will basically confirm if everything's been installed correctly. Excuse me. So here we're simply importing the Torch library. And then the first print statement checks if we have a GPU available. So if we've installed CUDA toolkit and we have a compatible GPU, then this should return true. So let's wait a bit for it. So ayan. So you can see that the PyTorch was able to detect my GPU. We can also check how many GPUs are available. So in this case, I'm running this on laptop, so I only have one GPU. And then we can also check the current GPU that we're using. So if you have multiple GPUs, you can switch between them. In my case, I only have one, so I'm using GPU 0. So that's essentially it for setting up your PyTorch environment. Make sure that everything's been installed correctly in order to be able to use the GPU for training. So now that we have the environment set up, we can move to the next section, which is preparing our dataset. So I included the dataset that we'll be using in the notebook. So we'll be using the MNIST dataset. So for those of you who are unfamiliar with MNIST, it's a dataset that contains images of handwritten digits from 0 to 9. So we can see from the dataset folder, it's divided further into a training set and a test set. If we look at the contents of one of the folders, we can see that the images are divided into the different categories. So we have images that are 0, images that are 1, all the way up to 9. So we can check a sample image. Ayun, so this is essentially what one of the samples look like. It's basically a handwritten digit. So in this case, when our data set, we have different methods for preparing our data set, which will depend on how our data set is structured. So in this case, since we have our images that are divided by the classes that they belong to, we can use method 1, which uses the image folder class of PyTorch. So the image folder basically processes the data for us. So it separates the images and from the labels, which will depend on the subfolder that they're located in. So that's why it's important that the images are already divided into the different classes. So to use the image folder, we have to call it first using from the datasets module, and then we pass it a few parameters. So the first parameter is the file path to the the folder path to the dataset. And then the second parameter that we have to pass is the transform. So this parameter applies transformations to our data before it passes it back to us. So why do we need to transform our data? By default, our data or the data that we're working with is in the data type of images, right? It's in the form of an image. So we need to convert that into a data type that PyTorch can process. So in this case, PyTorch mainly uses tensors. So tensors is basically an array that can be used in the GPU. So to convert our images into a tensor, we can use the built-in function from the transforms library called toTensor. So this essentially turns our images into a 2D tensor. So aside from converting it to a tensor, this also, sorry, I'll just delete this. So aside from converting it into a tensor, it also changes the range. So usually for images, the pixel values are in the range of 0 to 255. But we want to decrease that range to a range of 0 to 1. So we do this in order to decrease the computational complexity, since we're going to be working with smaller numbers as opposed to the full pixel range. So that's the first transformation that we typically do. Another transformation that you might want to look into is to normalize the images. So sometimes in the dataset, there could be variance between image samples. So for example, in images, right, the lighting conditions may not be the same for each sample. So in order to reduce the variance between samples, we usually normalize their values. So we usually do this by manually computing for the mean of the samples and then dividing that by the standard deviation. But for the sake of this workshop, we're going to use the normalize function, which can also be found in the transformations library. So for the normalize function, all we have to do is pass it the mean value of the images and the standard deviation. So for these values, I didn't compute them. So since we're working with a standard benchmark dataset, which is the MNIST, you can actually just search up the values yourself. If you want to compute for these values, it's also fine. But for this case, I simply just searched what was the mean value and what is the standard deviation. So that's basically how to use the image folder. So this class will basically process the data for us. It will separate the images from the classes. So we do this for each of our partitions. So since we have a train set and test set, we have to create a data set for each, right? So here we're creating one for the data set, and then here we're also creating one for the test set. So we can run this. Actually, I forgot to transform also the test set, so I'll do that now. So let's run this and wait a bit. Ayan. So now that it runs, we can actually check also the length of our data set. So since the data set is basically just an iterable, we can just print the length of it. So length, train set. And then we can also check the train data. And then we can also check the length of the test data. And then here. Ayan. So as you can see, there's 60,000 samples in the training set, while we have 10,000 samples in the test set. So that's good. We know that the code works. So this is only the first of the methods that we can use. Normally, we use image folder when our data is already divided into the different classes. But there are times when the data set sort of groups up all the images into one folder. So you don't necessarily know which class an image belongs to. So normally in those cases, what the authors of the data will provide you, they'll provide you with an additional file. So it's usually an annotations file that will tell you which class does a particular image belong to. So as an example, we have two annotations file here, one for training set, one for test set. If we look at the contents of one of these text files, we can see that for each line, it contains the image name or the image path, as well as the corresponding labels. So this essentially tells you which sample or which data set does the sample belong to, and what's their corresponding classes. So in the cases where you're provided with an annotations file, you'll have to create a custom data set in order to import your data. So to create our own dataset class, we have to first instantiate a class, and we have to make it inherit from the dataset library. So here we're simply instantiating a class called custom MNIST, and then we're inheriting from the dataset library. Then there are three functions that we need to override. The first is the initialize function. So in this function, this is where we define the variables that we'll need for the succeeding functions of the class. So in this case, I'm passing it a few parameters that I might need. Honestly, the choice of parameters for the initialize is up to you, depending on how you want to process your data. So in my case, I'm passing the file path to the annotations file. I'm passing the image directory, and then I'm passing the image transformations that I need to use. So for the initialize function, I'm simply opening the annotations file. And then for each line, I'm basically separating the image name from the respective class. So here, I'm going through each line, and then I'm separating the image names from their corresponding classes. Then I'm also storing those image names into a separate array along with their corresponding classes. So this makes it more useful for the second function that we need to override, which is the length function. So the length function essentially just returns how many, the number of samples in the data set. So in this case, since we already stored the image names in an array or list, we can simply just return the length of that list. So that's it for the length function. The last function that we need to override is the get item. So the get item takes in an index as a parameter, and it returns you the image and its corresponding label at that index. So here we can see that it's returning a tuple. So in this function, this is sort of the function that you have the most freedom in implementing, since it will depend on how you want to process your data. In my case, I created helper functions to make the code more organized. But what I'm essentially doing is I'm taking the image given the index, and then I'm basically reading it using the CV2 library, and then I'm converting it into the data type that I need. So I'm applying the image transformations that I passed as a parameter. So that's about it for the custom dataset. It takes more effort to implement compared to just using the image folder, but you have more flexibility here on how you want to process your data. So for the less popular datasets, or for the more niche datasets that don't really follow a standard format, you'll have to create your own dataset class for it. So once we define our class, we simply just call it, and we assign it the parameters that we define. So that's about it for method 2. I won't run this code, since for this workshop, we'll use method 1 since it's more convenient. There's also a third method for importing the datasets. So if you're working with a common benchmarking dataset, for example, MNIST, or if you're familiar with CIVI, you can check the PyTorch library if they already have it imported. So in this case, we can see that the datasets have the MNIST dataset that we're using. We can simply ask PyTorch to download it for us. So the good thing with this method is that we don't have to download the dataset ourselves. As in, we don't have to search for it and then download it manually. We can simply import it from PyTorch, which will do the downloading for us. So in this case, we have to pass it a few parameters. The first parameter is the root directory. So if I recall correctly, this is always set to data. The next is whether or not we want the training set or test set. So if we're dealing with both, we have to create one data set for each partition. Then we have to set download to true, since we're asking PyTorch to download it for us. And then we're also passing it the transformation. So I think that's about it for the methods. Obviously, the easiest method here is method 3, since you can ask PyTorch to download it for you. But this will only work if your dataset is located in the PyTorch library. So you have different methods to choose from, and it will all depend on the type of dataset you're working with. So aside from the dataset, we also have to prepare data loaders. So usually, or normally in machine learning, we don't pass our data in one batch, as in we don't pass it all to the model all in one go. We usually divide the data set into batches and then feed those batches separately to the model. So this is what the data loader does. It essentially splits the data for us into batches. All we have to do is pass it a few parameters. So the first is the data set. So in this case, we're passing both the train data and test data that we defined earlier. And then we have to pass it the batch size. So the batch size refers to the number of samples you want per batch. So in this case, we specified 64. And then you can also specify shuffle. So this just shuffles the data before it splits your data into batches. So we can run this. Ayan, so it ran correctly. So that's about it for the first section. So to recap, the first thing we need to do is import our data. The method that we pick depends on, first, the format of our data set, and second is how we want to process that data. So if you want a convenient way, you can use method 1. But if you want sort of more flexibility in terms of implementation, you can go with method 2, which is creating your own dataset class. Once we have our data set, we then have to prepare our data loader, which essentially just splits our data into batches. So moving forward, this is the main variable that we'll be using in order to retrieve our data. So if there are no questions for this section, I'll move on to the next, which is loading pre-trained PyTorch models. So PyTorch has a full library of existing models that you can import. We can check the documentation, which I've linked in the notebook, or we can also print out a list of available models. So here you can see that there are popular models that PyTorch has in its library. So we have AlexNet, CovNext, ResNet, BGG, etc. So once we have a specific model that we want to implement, all we have to do is simply call that using from the models library. So in this code, we're using the models library and we're specifying the type of model that we want to import. Then we have to pass it a couple of parameters. The first parameter is regarding its weights. So PyTorch already trained these models. So if we want, we can use the pre-trained weights that PyTorch has. But if we want to train it from scratch, we can specify none. So with this parameter, we'll be training the model from scratch. So it hasn't learned anything yet. If we specify the default value, this will reference the latest version of the weights that PyTorch trained. So there are different versions of weights. We can choose a specific version by simply referencing it. So for example, we want a specific version of ResNet. We can do models.ResNet 50 weights, if I recall. ResNet 50 weights. And then here there are different versions. So we can see that there are versions 1 and versions 2. So version 2 is the latest trained weights. We can also select version 1 if we ever choose to, right? So that's something that we can do. But for now, we'll stick with the default weights, which is the latest version. The progress parameter, you don't have to worry about this. So when you import models for the first time, PyTorch first downloads it into your device. So the progress parameter just shows you a progress bar to see how far along that download is. So that's about it for the model. So we're simply just calling the model from the PyTorch library. The only real thing that we have to modify is the last layer, which is the classification layer. So for machine learning, or for CNNs at least, the output will always be a matrix with the same number of columns as the number of classes in your dataset. So what do I mean by that? So in our case, if we have 10 classes, then given one image input, our model will output a row with 10 columns. And each column will represent the probability that that image input is belongs to that specific class, right? So since we're using pre-trained networks, PyTorch trains these models on a dataset called ImageNet1K. So by default, the models output 1,000 classes or 1,000 columns, right? So it doesn't match our dataset. So to fix this, we have to change the last layer, which is the classification layer. And then we have to modify it to use the correct number of output features. So to do that, I'm simply referencing the name of the last layer, which is FC. And then I'm assigning it a new type of layer. So I'm assigning it a linear layer that takes in 2048 features as input. And I want it to output 10 features. So 10 columns, one for each of our class. So a couple of things to keep note of here. So number one, how do we know that the name of the last layer is called FC? And then number two, how do we know that it takes in 2048 features? So I'll comment this line of code out first. So we can actually print the model to check its structure. So if we run this code, so we can see that it prints out the different layers of the ResNet 50 model as as well as their different parameters. So if we scroll to the very bottom of this output, we can see that the last layer is called FC. It's a linear layer that takes in 2048 inputs and outputs 1000 columns. So this is by default since it's trained on the ImageNet 1K. So knowing this, we can now reference the last layer. We know how many input features we need to feed it, and then we can simply just change the output features, right? So before modifying anything, it's first important to check the structure of your model. So for example, we can check a different model called EfficientNet V2M. So this will obviously have a different structure. And depending on the structure, we may have to edit this line of code. So in this case, if we print out the full output, we can see that the last layer is called Classifier, and it's in the form of an array. So in order to reference this, we'll have to do models.classifier. So this references the last layer. And then since it's an array, we have to actually index it. So since we're looking at the last element of the array, we'll index it with 1. And then for the input features, it's also different, right? So here, the input features that we need to take is 1280. So that's what we'll input. So that's essentially it for importing models. For the sake of this demo, we'll stick with the default ResNet 50. So we'll use ResNet 50 with pre-trained weights, and then we'll modify the last layer. So if we run this code, we can see that the last layer has changed. So it still takes an input of 2048, and then it outputs 10 features. So these represent the probabilities for each class. So that's essentially it for using existing models. I'll also talk a bit about creating your own model from scratch, or if you want, you can use an existing model as backbone, and then we can build on top of that. So to create your own model, we first have to define a class for it. So we define a class, and then we have it inherit from the nn.module. Then there are a few functions that we need to implement. The first is the initialize. So in this function, or in this portion of the code, we're simply defining the layers of our network. So in the previous output, we can see that each layer is basically composed of layers, or each network is basically composed of layers. So that's essentially what we'll be defining in this class. So you can either start from scratch, as in define layers without a pre-built network, or you could specify an existing model and then use that as part of your network. So we call this the backbone of the network since we're using an already existing model. So in this case, I'm importing the ResNet 50 model, converting it into a list in order to make it easier to process. And then I'm taking all of the layers except for the last two. So if we recall, the last two layers are only pooling layers and fully connected layers, which we don't necessarily need for creating our own model. So once I extract those layers, I assign it to my own backbone layer for the model. And then on top of that layer, I'm defining additional layers. So I won't go in depth on what's the purpose of each layer, since it's a lengthy discussion then. So just know, for CNNs, we mainly deal with convolutional 2D layers. So this is what your network will be comprised of majority. So aside from that, I'm also specifying activation layers, and I'm also specifying a classification layer, which we have to set according to the number of classes that we output. So that's for initializing the model. The other function that we need to implement is the forward. So in machine learning, we refer to this as the forward pass. So this function essentially passes the input through each of our layers. So X is the input, and all we want to do is we want to pass it through each layer. So the input of one layer is basically the output from the previous layer, right? So that's essentially what the forward pass does. And then at the end, we're simply returning the output, the final output of the model. So once we define our class, all we have to do is instantiate it, right? So this is instantiating the model. For the sake of this demo, we'll be using the pre-trained model since it's more convenient and it's already been trained. So you can expect higher results compared to when you train a model from scratch. Okay. So if there are no questions for this portion, I'll move on to the next section. But feel free na lang to chat if ever may tanong kayo. So the next section talks about loss functions and optimizers. So these are other two components that we need in order to train our model. So the first is loss function. So for those of you who are unfamiliar with machine learning, the loss function is essentially the metric that we use in order to measure how well our model does. So what this does is it takes in the predicted outputs and it tells us how close or how far it is from the actual correct answer. So it gives us a loss value that we want to minimize, right? We want our model to produce a small loss value or small error value. We want to make it as close to zero as possible. So there are different types of loss functions to use. For multi-class classification, we usually use the cross-entropy loss. So that's what we'll be using for this workshop. So we basically call the cross-entropy loss from the NN module, and then we're assigning it to a variable. The other component that we need is the optimization algorithm. So the optimization algorithm is what takes the loss value and it computes the gradients. So the gradients are what we use to update the parameters. So this essentially is what helps our model to learn, right? So throughout the training process, this is what actually makes the model learn. So it continually updates the parameters depending on the loss function. So again, there are different types of optimization algorithms that you can use. For this workshop, we're using the commonly used SGD, which is the stochastic gradient descent. And we have to pass it a few parameters. So the first thing we have to pass is the parameters of our model. So this is how we tell the optimization algorithm which parameters or which weights to update during training. The next thing we have to specify is the learning rate. So the learning rate is basically how big of a step or how big of an update does the optimization algorithm do. So we initialize it to a value of 0.01. So you can change this. These are just hyperparameters naman. So you can change it accordingly to your own project. And then we also have another parameter here called momentum. So momentum's another parameter that affects the sort of the size of the update that the SGD takes. So that's a gist of the parameters for SGD. So we simply run this to initialize the loss function and optimizer definitions. So I think you can tell by now that most of the things that we're doing is really abstracted, right? We're not really coding anything or we're not really implementing the full functionality of what a loss function is or what an optimizer is. So PyTorch makes it easy in the sense that we can simply abstract these methods and call it from the library. But I still think it's also a good idea to at least learn what happens underneath the hood. So if you want to learn more about what the functions actually do, you can always check the PyTorch documentation since it's comprehensive and it really tells you more about what's going on with the functions that we use. So that's it for the loss functions and optimizers. The next thing that we'll look at is the training loop for the classifier. So in this case, the first thing we have to do is define a few variables that we'll use for training. So the first variable that we define is the number of epochs. So this serves as our sort of stopping criterion of how long we should train the model for. So one epoch is equivalent to the model processing the, one cycle of the data. So you usually want to train the model for more than one epoch, but for the demo, we'll only train it for one epoch since it does take a while for it to train since I'm only using my laptop GPU. So for this demo, we'll only set it to one. In terms of knowing the proper value to set the epochs to, this usually depends on the programmer. So there's no right way of or there's no right value to how many epochs you have to train your model for. It's usually through experimentation, trial and error, or reading reference works and using their configuration. So it's up to you, the programmer, to sort of figure out which or how long you should train your model for. The second parameter that we define is the model save. So this acts as a checkpoint of when we should save the weights of our model. So I'll discuss this more in depth later on. But for now, just know that this serves as a checkpoint variable for our training. The next parameter, or the next variable rather, that we define is the device. So by default, PyTorch doesn't use our GPUs for training. We have to tell PyTorch to use it, or we have to move the data into the GPU in order for PyTorch to actually process it. So here, what we're doing is we're passing a Boolean argument here that essentially means that if a torch or if a GPU is available, and if CUDA can, or if PyTorch can access that GPU, then we'll set the device to that GPU. If not, then we'll use the CPU. So this makes your code more robust in the sense that it can run using either GPU or CPU. Though keep in mind, if you use CPU, you'll be limited and it will be resource intensive on your end. So that's essentially the device variable. So now that we set the device that we want to use, we have to move our variables to the device. So anything that interacts with our data has to be on the same device as the data, right? So if our data is located in the GPU, then our model, our loss function has to be in the GPU. If the data is located in the CPU, then our model has to be on the CPU along with our loss function. So basically just ensure that they're both on the same device in order for them to interact with each other. So here we're simply moving the model and the loss function to the device that we set. So that's what the to function does. So those are the variables that we have to define. You can always define more variables according to how you want to implement your training code. But in this case, these are sort of the main variables that you at least need to define. So now let's move on to the actual training of the model. So the first thing that we do is we initialize the loop. So we're essentially initializing the loop for as many epochs as we specified. So in this case, we're only training it for one epoch for now. Then the next thing we have to do is we have to set the model to training mode. So there are two modes for the model. So there's training mode, and then there's also model.eval mode. So the reason for two different modes is that different layers perform differently depending on whether you're training the model or you're testing it. So I'm not sure if you're familiar with the concept of dropout layers. So dropout layers are a type of layer in machine learning that essentially zeroes out or deactivates some of the nodes in the network. The gist of this is, the intuition behind this is basically to avoid overfitting. So during training, you want the loss, or you want the dropout layers to be active, right? But during evaluation mode or during testing, you want to deactivate the dropout layers because you want all of the nodes in the network to be active. So that's essentially the importance of setting our model to the different modes. So in short, for training, syempre set the model to training mode. For testing, set it to evaluation mode. And then we're also defining running loss. So this is sort of another metric that you can display during the epoch or during the training. So this just tells you sort of whether or not your model is actually learning from the data. Since it's a running loss, we want to minimize this, right? So if you observe that the running loss throughout the training is actually increasing rather than decreasing, then you might want to reconfigure some of the parameters of your training. And then aside from that, we also have this block of code. So this essentially updates the learning rate. So in machine learning, right, we specified an initial learning rate. Throughout the training process, however, this learning rate will gradually decay, or it will gradually decrease, right? So when it comes, we usually want to set this to towards the end of the training. So let's say we have 120 epochs. We usually want to set this towards the end, so maybe 100 epochs. And what this does is it significantly decreases the current learning rate. So the intuition behind this is that during early stages of training, since our model doesn't really know anything yet, we wanted to take bigger steps toward the right direction. So towards the end of the training, once our model has learned, or we assume that our model learns majority of the data set, we want to lessen the step that it takes in order to sort of fine tune it, right? So that's why we decrease the learning rate. So you don't necessarily have to worry about this for now, but once you get into sort of the specifics of training your model, this is a helpful piece of code. Okay. So for the main portion of training our models, it's actually this whole block. So let's dissect this line per line. No? So what we're doing is we're first creating a loop. So the train data loader that we've defined earlier is basically an iterable, right? So this returns us a pair of images and their corresponding labels. So you don't have to worry about the TQDM. So this is sort of an additional function that shows you the progress of how far along your data, of how far along your model is. So it's nice to have so you can see the progress of your training, right? So again, the train data loader, we're iterating through it. And for each iteration, we take a pair of images and labels. So these are our data. What we need to do to that data is we need to move it to the device that we set. So here, assuming that we set the device to the GPU, we have to move the images and the labels to the device. So this part of the code moves it to the GPU in order for the model to be able to process it. So that's that. The next line of code optimizes at 0 grad. So this essentially empties the gradients before we proceed with feeding the input to the model. So why do we need to zero out the gradients? So gradients are basically the values that we use in order to update our weights, right? So we compute for the gradients and it tells us how far do we need to move in a certain direction in order to get a better performance result. So since we're doing this by iterations, we need to first empty out the gradients since there could be residuals left in the previous iteration. So this is something we always have to do before actually passing the inputs. So keep that in mind. The next line of code is basically the forward pass. So the term forward pass just means that we're passing the input through each layer in our model. So in this case, we're taking our model and we're giving it the images that we took from the data loader. So if you recall earlier in the workshop, here for defining our custom class, we have to define a forward function. And this forward function is what passes our input to the data. So that's essentially what the model is calling when we pass it our inputs, right? So we don't necessarily have to do model.forward, right? We can simply just do model and then pass it our input images. So we store those outputs into a variable, and this will be our predicted results, right? The next thing we have to do is we have to measure how good those predicted results are. So this is where we use the loss function. Remember that the loss function is basically the metric of the performance of our model. So it measures how close our predicted results are compared to the correct answers or the ground truth labels. So here, we're passing the loss function. We're using the loss function. We're passing it the predicted outputs that we had. And then we're also comparing it to the ground truth labels. So these are the labels that contain the actual correct classification answers. So the output of this will be a loss value. Now, our objective is to minimize this loss value, make it as close as possible to 0 as we can. So once we have the loss function, we can compute for the gradients using backpropagation. So all we have to do is call the backward function, and this will compute the gradients for us. Normally, or under the hood, this will take mathematical equations, right, to compute this manually. So again, with PyTorch, most of the things are abstracted for us. So in order to do backpropagation, all we have to do is call .backward function from our loss. So this will compute for the gradients. Now, the gradients are what we use in order to determine how to update our parameters. So once we have the gradients, we take our optimization algorithm and we call .step. So .step is essentially what updates the parameters for us. So if you recall earlier, we passed the model parameters to the optimizer. So the optimizer knows which layers or which weights does it need to optimize or update. So that's essentially what this line of code does. And then here we're simply just keeping track of the running loss. So again, this is just another metric that we can use to evaluate the training of our model. So that's essentially it. So this essentially happens for each batch in our data and for each epoch that we set it to. I've commented this line out, but I'll uncomment it. So assuming that we finished one epoch, so basically our model has gone through the entire data set once, the next thing we want to do is we want to save the weights. So this code is dedicated to saving the weights that we've used for training. So why is it important to save weights, right? Because you can honestly just train the model and then you can go directly into testing. So why do we have to save the weights for it? The reason for that is to be able to replicate our experiments. Because if we don't save the weights, what we'll have to do is every time we want to test our model, we'll have to first train it. If you have 100 epochs, you'll first have to train it for 100 epochs, and then you'll have to test it, which may even produce different results, right? Because it's not entirely stochastic. So by saving the model weights, we can ensure that every time we want to run experiments, we can simply just load the weights into the model, and it will produce us the same results every time. So that's number one. In this case, we're using a checkpoint variable. So remember earlier, we defined a checkpoint variable. And this tells us how many epochs do we want to save weights. So this is good, especially if you're working with a long epoch amount. So for example, if we were to train the model for 100 epochs, right? Our model will have to go through 100 epochs straight without stopping. Now, there are times when something unexpected happens. For example, your PC crashes or there's a power outage. So in those cases, right, what you'll have to do is you'll have to start from scratch. So in order to sort of prevent that, we set a checkpoint variable. And this tells us how many epochs do we want to save our model for. So in this case, if we specify the checkpoint to 10, this means that it will save the model weights every 10 epochs. And what that does is it allows us to, if our training suddenly stops, we don't have to start from scratch. We can simply just load the last save weights and then resume training from there. So for example, if we're currently on epoch 85 and our model suddenly stops, we don't have to start again from epoch 0. We can use the weights saved on model or for epoch 80 and load that into the model and then continue training from there. So that's essentially the purpose of having a checkpoint to when to save your weights. That's essentially it for the training. So to recap lang, we have to first define some variables that we'll use for training. We then start iterating through each epoch. We set the model to train mode, and then we cycle through our data loader. So for each batch given, we have to move those data into the GPU. And then basically this is sort of the standard flow. So we first zero out the gradients. We then produce outputs by passing the input to the model. We then measure how far those outputs are from the ground truth labels by calling our loss function. And then we have to compute for the gradients using backpropagation. And then we update the weights using the optimizer.step. So we'll run this whole training loop. It may take a while since honestly the training it depends on the device that you have. So even though I'm using GPU, it still takes a while since I'm on laptop. So that's why we're only running it for one epoch. But just to show you of sort of what the output should look like during training so that you're aware, we'll run this. So let's wait a bit na lang for this to finish. If you have any questions pala about anything that we discussed so far, feel free to message the chat. Ayun. So as we can see, it started training. So this is the result of TQDM. So the TQDM is what produces this progress bar. Ayun. So it might take a while talaga since ayun. So siguro, ayun, I'll explain siguro the output then. So 938 is basically the number of batches that our data is split through. And then it also shows you sort of the how long does it take per iteration. So one iteration is basically one batch. And then it shows you sort of the estimated time. So ayun, this may take a while talaga. So let's just wait for it for now. Yep. I've also prepared pala. So while waiting, I've also prepared a folder of where to save the weights. So in this case kasi, right, for saving the weights, actually I didn't discuss this part. So for saving the weights, we use the torch.save function, and then we pass it two parameters. The first parameter that we pass it is the state dictionary. So the state dictionary of the model essentially holds the different layers as well as their corresponding weights. So we have to save this is essentially what we're saving. The next thing we have to pass is the path to the file that we want to save it to. So here, I basically created I defined a path variable. So this essentially tells it to save it in the folders called weights. In that folder, we have another folder called ResNet50. And then as for the name of the file, we're assigning it the epoch number. So the extension for weight files is normally PTH. So whenever you save your weight file, it will always be the name of the file .pth. So this should save our file as one.pth, right? So siguro let's wait for this. I should have ran this siguro earlier, but ayan. See, siguro, so to save time, I guess I could also talk about the testing loop now while this is run. So the testing loop is honestly the same as the training loop. There are slight modifications now. So for the training loop, again, we have to first define a few variables. So here, we're defining the device that we want to use, and then we're also moving the model to that device. Notice that we're no longer using the loss function. So you could still use the loss function if you want to check the loss between the test results and your predictions. But in our case, we're not really concerned with that. I'm also defining a few variables in order to store the predictions and the ground truth labels. So this is more for producing metrics later on. So later on, we'll be using libraries such as sklearn in order to produce a result report, right? So assuming that we have our models trained na, we have to load the weights into the model, right? So to do that, we first have to read the weights file. So, and assuming that we've already saved it, it will be located in the weights folder, in the ResNet50 folder, and then underneath the name one.pth. So this essentially reads the pth file and it converts it into a state dictionary. And then we load that state dictionary using the load state dic function. So that's essentially how we load the weights to a model. And then as mentioned previously, since we're testing, we have to set the model to evaluation mode, right? So this is to deactivate some of the layers that might behave differently during training. So the next thing we look at is the main loop. So here we're specifying torch.nograd. So normally during training, I think this is by default. When you pass inputs to the model, it will actually compute for the gradients. Now recall, the gradients are what we use in order to update our weights. But for testing, we don't necessarily want to update our weights, right? We just want to see how well our model performs. So we have to specify torch.nograd so that it doesn't compute for the gradients. Aside from that, it's basically the same loop. So we're using the test data loader that we defined earlier. And then again, it returns us a pair of images and labels. We have to move those data into the same device as our model. And then we simply produce outputs by passing the images to our model. This is sort of the main difference. So here, our output, as I said before, right? So for machine learning, the output of classifiers is a matrix with the same number of columns as your target class or as the number of classes that you have. So this represents sort of the probability that a sample belongs to one of those classes. What we want to do is we want to take the maximum probability, right? Since that's sort of our prediction that the model thinks that this class or this sample belongs to this class the most. So to do that, we can take the maximum value across each row, and that will form our prediction. So this is essentially what this line of code does. It takes the maximum probability from each row, and we use that as our prediction. And then here we're simply just storing the predicted values and the true values into an array or into a tensor rather. So we do this for all of the samples in the data set. So as you can see, it doesn't really give you anything, right? We're simply just performing testing, and then we're storing the results in a separate array. And then here, we're moving recall that these variables are in the GPU currently. So since we want to use NumPy, or we want to use sklearn to create our metrics, we have to first move the tensors back to the CPU. So if you want to use your variables with outside functions, it would be best to first move them back to the CPU, since tensors are the GPU specifically used by PyTorch alone. So that's the reason why I moved it back. Anyway, the training's done. So as we can see, it's complete. It took about 6 minutes, and that's with using GPU pa. So it could take a while talaga, depending on the specs of your device. So for one epoch, we've accumulated a loss of 0.44. So some researchers use the loss in order to tell how well their training's going. So what they'll do usually is they'll train the model for a few epochs, and then they'll take note of the loss to see if they need to change any configurations. So that's something that you can do in order to fine-tune your parameters. So if we check the weights folder, we can see that we have a file called 1.pth. So this is our save weights. So I'll run this now, so since it might take a while. So again, so we move the results back to the CPU in order to produce our metrics. So this is how we can compute for the different metrics that we want to use. These are basically just built-in functions from the sklearn library. Siguro while this is running, I can explain. So accuracy score is what you would expect. So this is basically how many samples did you get correctly out of the total number of samples. Balance accuracy is sort of the same idea, but it gives more importance to the samples with less, or to the classes with the less samples. So ideally, you use this for imbalanced data sets, right? So an imbalanced data set is when your classes don't necessarily have the same number of samples. And then aside from that, you have different F1 scores. So I'm not sure if you're familiar with the precision and recall, but the F1 score sort of computes for the balance between those two metrics. And the F1 score in this case takes the average among the different F1 scores of the classes. So F1 micro is basically the same as accuracy, so you don't have to worry too much about it. F1 macro is the average among the different F1 scores of each class. And then F1 weighted is essentially the same as F1 macro, but it gives more importance to the classes with less samples. So in the case you're working with an imbalanced data set, this is also a good metric to use. So we've printed out the results. So ayun, actually, as you can see, our test data had 157 batches. And even though we only trained our model for one epoch, we were able to get a high accuracy of 98%. No? So that's sort of the main advantage of using pre-trained weights. So it's always better to use pre-trained weights rather than to train your model from scratch. And that's because your model already learned something, right? So it's not learning from zero. It already has sort of a stepping stone in order to further learn more. No? Ayun pala, sorry. There's a few questions pala. So first question, in real life scenarios, is it really a lot of just waiting? In real life scenarios, is it really a lot of just waiting? So if you mean waiting in terms of the training, then yes. That's why it really takes a while depending on the number of samples you have in your data set. So in some cases, it could take hours. In other cases, it could even take days, depending on the number of samples you have and the configuration or the specs of your GPU. No? So, ayun, keep that in mind na lang if you're employing some of your projects. So, you have to also consider sort of the time allotment that you have to train your models. There's also another question, how are the weights loaded? So ayun, we load the weights using this function in particular. So the first thing we do is torch.load. So this function, let's separate it now. So this function essentially reads the file. It reads the file and it converts the contents of the file into a dictionary. We then take this dictionary and then we load it into the model using this function, load state dictionary. So that's essentially how we load the weights into the model. So it's a two-step process that you can combine into one, right? So you're reading the file and then you're loading the dictionary into the file or into the model, sorry. So I hope that answers your questions. Ayun. And then that's basically it for the metrics. So these metrics are normally used as an overview of the entire data set. What we can further do is we can actually look into the individual class accuracies in order to better understand the performance of our model. So here we're using additional functions from our sklearn library. So we're going to be creating a confusion matrix as well as a classification report. So we can run this. So in this case, although this is helpful, it's not entirely accurate. So as you can see, almost all of the values are rounded off now. So it does give you a good approximate, but if you want sort of super accurate details, then you might have to compute for these yourself. So siguro to give you an idea of what each metric means, the precision score relates to how many false negatives did your model produce, right? So for example, out of all the classes that you predicted 0, how many of those samples weren't actually 0? The second metric, recall, tells you how many samples did you get correctly given a class. So given, for example, 60 or given 10,000 samples of the samples that belong to the class 0, how many of them did you actually get correct, right? So the F1 score basically just gives you sort of a balance between these two. And that's basically it naman. There's a question sa chat. After training and testing, how can we use the model to predict? So actually, we're already using that. So here in the model, right, it's part of the testing. So this line of code basically gives us our predictions now. So for example, for one input, right, it will give us a output that is 1 by 10. So it's a 1 by 10 vector now. So why is it 1 by 10? So this basically gives us the probability scores of each class, right? So since we have 10 classes. Now, it gives us probability scores, but it doesn't give us the predicted value. So to get the predicted value, we usually get the maximum probability, which is what is happening in this code. So if you want to use it for prediction, without necessarily testing it now, you basically combine these two lines. So you first pass the input, which could honestly just be one image now. It doesn't necessarily have to be a group of images. You can simply pass one image to the model. It will then provide you with an output of dimensions 1 by 10. So those 1 by 10 is the probability scores of each class. And then we want to take the maximum probability, since the model believes that, okay, this sample has this probability that it belongs to this certain class. So that becomes our prediction. So we want to take the maximum value among the rows. I hope that answers your question. Yeah. So essentially, we're already predicting using during our testing phase now. It's just that we're predicting using batches of images rather than a single image. But this should work regardless of how many inputs you pass to it. Hopefully that clarifies your question. Ayun, then going back to the metric. So again, you could use different libraries if you want to perform metric analysis. So in this case, we're outputting the classification report as well as the confusion matrix. We can see that even though we only trained it for one epoch, since we're using a pre-trained model, it will provide relatively high accuracies now. In fact, actually, it's sort of low then, since I think if you train it fully, you should be able to get an accuracy of 99, close to 100. So ayun, those are the metrics that we can use. So we can either have metrics that cover the entire data set, or we can delve deeper and look at the metrics for a specific class. No? So it really depends on the type of analysis that we're planning to do. So that's about it. We've covered all of the sections in our notebook. So again, you don't have to code anything yourself in this notebook in particular, right? Everything is coded for you. All you have to do is run it. This is meant to serve as a guide for you to build your own image classifiers. So if you want to sort of practice building your own, or if you want to test what you've learned in this workshop, I also included a separate notebook. So this is just a skeleton file. So I've labeled the different sections of the important portions of building your own image classifier. So use it as a guide in sort of implementing the model training and model testing yourself. Ayan, so there's another question. So hi, how can I detect overfitting during training? What metric should be checked on the output? Ayan. So I didn't include it here since I wasn't sure on how familiar are you guys with metrics and performance evaluation. But what usually happens is, so remember that we store the training or the running loss. So the running loss tells us how close our model is or how close our output is to the correct answers. So we want to minimize this loss to 0. So what people usually do is they take note of the running loss, and this is per epoch. So per epoch, we keep note of the running loss. Siguro you'll also create a list. So for example, loss list, right? And then this is where we'll append the loss per epoch. So siguro at the end of each epoch, we'll sort of loss list dot append running loss, something like this, right? So with this, we can actually plot this graph so we can plot the running loss over the number of epochs. To know if the model is overfitting, what you would have to do is you would also have to record the loss during training or during testing, or if you have a validation set, then you would record the loss over the validation set. And what happens is when you plot those losses, if you notice that the training loss continually decreases, but your validation loss sort of decreases and then increases, then it's a sign that during that epoch, the model starts to overfit. So I didn't include it here, but hopefully you get the explanation. So in terms of underfitting, if your training loss, when you plot it, if the training loss is continually decreasing, but your validation loss doesn't seem to decrease at the same rate, then that's a sign of underfitting. If your training loss decreases and then your validation loss also decreases, but there's a point when it starts to increase, then that means you should probably stop at that epoch. Because at that point, it probably means that your model starts to overfit the data. So yun, to keep it short, you keep a track of your running loss and then you plot it against the running loss of your validation set or test set, and then see if they observe the same trend. So you want them to both gradually decrease as you train your model for longer epochs. So hopefully that answers your questions. Oh, sorry, I wasn't able to show you an example. Ayun. So anyway, that's the overall workshop. So again, I provided sort of an assignment notebook. So everything's labeled here. What you can do is you can implement using your own data set. So whether you have your own data set or you import an existing data set from PyTorch, doesn't matter. You can also define your model, whether you use an existing one or try creating your own from scratch. And then define your loss function and optimizers. And then fill in the missing code lines for training and testing. And see if you can achieve a high accuracy on the data sets that you have. So that's about it for the workshop. Thank you for listening. I hope you've learned something. And I'll be sending the link to the code afterwards. I'll be sending it through the chat. And I think Sir Aaron will also send it via email along with the recording. So ayun, before siguro, there's another question. Ayun, so where can the notebook be found? So I'll be sending a link to the Google Drive. So it's a zip folder which you can download, and then it will contain both the notebook and the classifier, so or the assignment. So if you want to try editing the code, you can. I'll be sending it before the meeting ends in the chat. So ayun. Again, once again, thank you guys for listening, and I hope you've learned something. Thank you guys.
Thank you, Joseph. Are there any other additional questions before we end? Anyone? So Joseph was able to discuss how we train image classifiers. Especially, he also discussed 3 different ways on how to load your images or your samples or observations. It was also discussed yung loading of pre-trained PyTorch models. One of the things that was covered in the presentation, we also have discussed the different pre-trained PyTorch models. No? Pinakita niya rin kung paano mag-train and what do we replace sa classifier models if it's made in PyTorch. Papalitan natin yung last layer. All of those essential parts of training your models. So at least we hope by the end of this workshop, everyone is already ready to train their own classifier or image classifier. So I think there are no questions. So to end our workshop, let me first invite you to the next one. Thank you, Joseph, by the way. That's a good workshop for us. And let me show the next workshop. So the title of this is actually, since this is a series of workshops, you would imagine that there would be a part 2, no? Yung part 2 ng workshop ni Joseph would be held next term, not this term, but next term. But another workshop, this time on object detection, will be delivered by Carlo Azarcon, another BSMS student researcher under DLSU CIVI. So that would be next Wednesday. Sa calendar, that's October 23, which is for DLSU, that's week 8. No? So that's in 2 weeks. So if you're interested to join us again, you may look at our you may look at our Facebook page to learn more about the content of this workshop. No? The registration link will be posted there as well. So you just need to search for the Center for Computational Imaging and Visual Innovations, or DLSU Center for Computational Imaging and Visual Innovations.